Hi all, my name is P. Shekhar, Assistant Professor, Department of Electronics and Communication Engineering, Saint Martin Engineering College, Hyderabad. My topic is on Maxwell's equations for electrostatic fields. Maxwell's equations are the fundamental equations that describe the behavior of electric and magnetic fields. They are the cornerstone of classical electromagnetics. Here, electromagnetics may be regarded as study of interaction of charges at rest and in motion. It entails the analysis, design, interpretation, application of electric and magnetic fields. These electromagnetic principles find in various disciplines: microwaves, antennas, satellite communications, radar and meteorology, and also it includes various devices: waveguides, antennas, satellites, radars, electrical machines. So, to understand these devices require thorough understanding of laws and principles of electromagnetics. So, electrostatic fields. Here, Maxwell's equations formulated by James Clerk Maxwell's in the year 1860s. These equations describe the relationship between electric and magnetic fields, and also so with the help of Maxwell's equation, electromagnetic principles are generalized. So these are the four Maxwell's equations for static electric fields, of which first two equations are the Maxwell's equation that governs the static electric field. One is divergence of D vector is equal to rho v. Another one is curl of electric field intensity is zero. That is conservative nature of electrostatic field. Coming to the electrostatics, what is meant by electrostatic fields or static electric fields? These fields do not vary with time. These are produced by static charges or static charge distributions. It is fundamental concept. Okay. So these fields are created by stationary or rest charges or charge distributions. This electric field describes the force experienced by electric charge by another electric charge at rest. These are the key concepts for understanding behavior of electricity and magnetism, as well as their role in various phenomena like lightning, capacitors, and insulators. There are two fundamental laws that governs the electric fields. One is Coulomb's law. It is an experimental law. It is an experimental law formulated in the year 1785 by French colonel Charles D. Coulomb. It deals with a force exerted on another point charge. It deals with force due to point charge exerts on another point charge. Here, point charge by mean a charge located on a body whose dimension is very small, negligibly small compared to other relevant dimensions. It has unit of coulombs. Okay, it is large unit of charge. 1 coulomb is equal to approximately 16 to 10 to the power of 18 electrons. Why it is large unit of charge? Because 1 electron charge is equal to minus 1.6 into 10 to the power of 1.6 into 10 to the power of minus 19 coulombs. So here, Coulomb's law, it is one of the fundamental law. It is stated as the force between 2 point charges is directly proportional to the product of charges and inversely proportional to the square of the distance between them, and also it is along the line joining them. Mathematically, we can write F bar is equal to K Yes, Amit. Mathematically, we can write F bar is equal to here electric force between two points is directly proportional to product of charges magnitudes and inversely proportional to square of the distance. So we write F bar is equal to K times Q1 Q2 by R square, where K is constant of proportionality. So it is magnitude. Sorry. F bar, this force directly proportional to Q1 Q2 by R square, that is given by K Q1 Q2 by R square. In SI units, Q charges having units coulomb, or distance between charges in meters, so that K value is 1 by 4 pi epsilon naught, where epsilon naught is constant of proportionality, where epsilon naught is permittivity of free space. Permittivity of free space. It has value 8.805 into 10 to the power of minus 12 farad per meter. Force having units in newtons. Mathematical vector form. Let us, if two charges located at 2 points with the position vectors r1 and r2 from origin, let us, this is the force between two charges is along the line joining them. It is vector form. We can write F bar is equal to force on second charge due to first charge is given by F1 2 bar is equal to 1 by 4 pi epsilon naught Q1 Q2 R square AR bar, where AR bar is unit vector, along the line joining them, that is magnitude of R2 bar minus R1 bar R2 bar minus R1 bar divided by magnitude of R2 bar minus R1 bar. So it is the vector form. Next, electric field intensity. Electric field intensity, it is a point charge. Normally when we brought into another point charge, it experiences a force. It is nothing but a point charge contain a point charge having the field around it. Okay, so if see here, it is a source charge Q. Okay, it has some field around it. When any small test charge is brought near to it, so this source charge will exert a force on it. So each charge associate its own electric field. It can be visualized as this, where R is distance between charges. So we define how much electric field is defined as. We take reference as a unit charge. Okay, how much force exerted on unit charge? It is nothing but electric field strength. So for unit charge, it is same as nothing but electric field. It is electric lines of force. That is F bar is equal to E bar. So it is defined as electric field intensity or electric field strength is defined as force per unit charge when it is placed in the electric field, having units newtons per coulomb or volt per meter. Here we should note some important points. Here Coulomb's law is applicable only for point charges which are at rest. Signs of the charges taken into be account. The distance between the charge must be large compared to their dimensions. We do have electric fields due to, like point charges, we do have electric field due to different charge distributions, like point charges, we do have electric field due to different charge distributions like line charge, surface charge, volume charge. They are characterized by their charge densities, rho L, rho S, rho V. So we define elemental charge to find the electric field intensity at some point. So let us, elemental charge due to line charge is given by rho L dl, dq, rho S ds. Here dq is rho V dV. So in general, we define electric field due to continuous charge distribution. We can give generalized definition, that is dE vector at any point is given by dq by 4 pi epsilon naught r square AR bar as per Coulomb's law. So in order to find total electric field due to line charge or surface charge, volume charge, we need to integrate over the distribution. So we get total electric field intensity at any point as this, dq by 4 pi epsilon naught r square AR bar. This is the general expression for finding the electric field intensity due to the charge distributions. These are uniform charge distributions. Next, Gauss's law. Gauss's law, another fundamental law. It also governs the electric fields for symmetrical charge distributions. Even Coulomb's law also applicable for different types of charge distributions. Preferably, Gauss law method is mainly applied for finding the electric field intensity due to symmetrical charge distributions. Clear number. See here. So for continuous charge distributions, okay, we define quantity electric flux. It represents the flow of electric flux lines through surface, any arbitrary surface. It is a measure of number of electric flux lines of force passing a given surface. Mathematically, we can write psi vector, it is represented by psi, that is equal to surface integral of consider any arbitrary surface. It is placed in an external electric field. We define how much electric flux lines of force crossing a given surface, that is we known by electric flux. It is a scalar quantity, surface integral electric field vector E bar dot ds bar. Another quantity we do define, that is that is surface integral of d bar dot ds bar. For practical reason, we consider this expression because this expression is independent of medium where charges lies, where d vector is epsilon naught times E bar. Here, each electric lines of force emanating from 1 coulomb charge and terminates on -1 coulomb charge. So it has unit coulombs. Hence, this electric flux has units coulomb. Therefore, d vector has the unit of coulomb per meter square. Hence, we call it electric flux density. Electric flux density. For historical reasons, we also call this vector as electric flux displacement, or we call electric flux displacement. Electric flux displacement. So here Gauss law is based on the generalization of Faraday's experimental law for determining the electric field. That is, it is applicable for closed surfaces. That is here. Yeah, Gauss law statement. What it states? Gauss law states that total electric flux through any closed surface is proportional to the total charge enclosed by that surface. So it relates, it is fundamental law, it relates the electric field to the distribution of charges. See, you can see the visual, one of the electric fields enclosed by closed surface. See, it is the one important property of electric flux. Always electric flux lines are emanate from positive charge and terminate on negative charge. So it is one of the Maxwell's equations to be derived for electromagnetic fields. That is, divergence of electric field measures the net outward flux of electric field at a point. Consider a closed surface . So there is a positive point charge Q. Always it emanates electric flux lines radially. As per Gauss law, total flux through any closed surface characterized by volume charge rho v. Charge is uniformly distributed over volume. As per Gauss law, total flux through any closed surface is closed surface integral of d bar dot ds bar is equal to total charge enclosed by that surface. So we write this total epsilon times E bar dot ds bar is equal to volume integral of rho v dv. By applying divergence theorem, by applying Gauss divergence theorem, we write, by applying Gauss divergence theorem, we write volume integral of divergence of d vector dot ds bar is equal to volume integral of rho v dv. So by comparing the integrals, we get the relation divergence of electric flux density is equal to the volume charge density. It is one of the first Maxwell's equations to be derived. First Maxwell's equation. Gauss law is applicable for finding electric field due to symmetrical charge distributions. So we do have various types of symmetrical charge distributions. Line charge, symmetrical line charge of infinite cylindrical charges, spherical charge distributions. So it is a Gauss's law for electricity. Next, another important concept is for electrostatic fields is electric potential. Up to now, for electric field determining, we have a laws, fundamentals laws, Gauss law and Coulomb's law. Another way of finding electric fields in space is way of scalar potentials, scalar electric potential and potential energy. So it is another important quantity for describing the electric field. What is electric potential? Electric potential at any point is the difference between electric potential at that point and reference point. Or another way we define by assuming potential at reference point are infinite as 0, the potential at any point R is defined as amount of work done by the external agent to bring the charge from infinite to that point. We call potential. Here potential energy is the potential energy of charge or test charge in an electrostatic field is the work done by the field to bring the charge from infinite to the current location. So it is the amount of energy stored in electric field due to the interaction of charge and field. Mathematically, we express here. Here we suppose to move the point charge from A to B along a path in terms of external electric field. There is some work has to be done. So as per Newton's law, we express how force exerted, force here Q into E due to, okay, and work done in displacing charge by elemental displacement dl by this expression dw is equal to minus f bar dot dl bar. So total work done by the field, we can write w is equal to minus q times line integral of a to b e bar dot dl bar. It is the total work done by the field, total work done on charge from A to B in the field. Here negative sign indicates that an external agent does the work. Here we define work done per unit charge, that is nothing but the potential in an electric field. Okay, so we define here potential difference between points A and B as the potential energy per unit charge. It is nothing but potential difference, that is line integral of A to B E bar dot dl bar. That is simply we write VB minus VA. Since we know that electric field due to source charge, that is Q by 4 pi epsilon naught R square AR bar, by substituting in the expression we get the relation VAB is equal to Q by 4 pi epsilon naught 1 by RB. That is here we write Q by 4 pi epsilon naught into 1 by RB minus 1 by RA, means that is VB minus VA. Here we should note some points here. The potential due to an electric field depends on only the initial and final points, and it is independent of path taken. After evaluating this expression, if VAB is negative, means there is loss in potential energy. So it is done by the field, work is done by the field in bringing charge from reference point to that point. If VAB is positive, there is gain in energy, so an external agent performs the work. So how it is potential is independent of path taken. So when we consider a path, while let us a point charge was moved from A to B and B to A, and by evaluating surface integral of E bar dot dl over closed path result 0, means total work done by the field in moving a charge along a closed path is results 0, means so each point on a path has the same potential. It forms an equipotential surface in the field. So net work done, no net work is done in the equipotential surfaces. That indicates the conservative nature of electrostatic fields. So by applying Stokes' theorem, we get the expression curl vector is equal to 0, means it is conservative nature of electrostatic field, or it is irrotational field. So these are the point charge and dipole and their associated equipotential surfaces, where each flux line indicates the direction of electric field. So another important where we find Poisson's and Laplace equations. Here electrostatic field problems, that is where some regions where when the two different regions where electric field exists, in order to determine electric field at the boundaries, so we call them electrostatic boundary value problems, where electric field requires either charge distribution or potential variation, but in such cases only initial static conditions are given. So in order to determine potential or electric field throughout the regions, so done by the with help of these equations, Poisson's and Laplace's equations, this relates the potential variations with the charge density. Here Laplace is special case of Poisson's equation. Next, boundary conditions. Boundary conditions defines the behavior of electric field at the interface between two different media. Also helpful determining the field if the electric field is known in another one region. Okay, so the conditions involve continuity of normal component of electric field and discontinuity of tangential component. So for solving the electrostatic problems often involves these conditions, and using different methods, numerical techniques, practical methods. Okay, we solve this electrostatic problem with the help of Gaussian and Laplace equations and boundary conditions. Applications of Maxwell's equation in electrostatics. These electrostatic fields finds in various applications, primarily solid state electronic devices, that is semiconductors, operation of capacitors, that is equipotential surfaces, where like example is capacitors, they store energy in the form of electric field. So these semiconductor devices, their operation mainly depends on electric field. Another example is medical imaging, where diagnosis is done with the aid of electrostatic fields. So finally, we conclude here, these Maxwell's equations play a vital role for understanding behavior of electric and magnetic fields. Also, they find various wide areas from design of electronic devices to astrophysical phenomena. So, understanding these equations provide deep insight into the nature of electromagnetism and its role in the world with us. Thank you.